Getting ready for this work.
Alright, so section 3.2 starts us into the discussion of measures of dispersion. Now again, much like we saw with the measures of central tendency, some of these things are things that you have already seen calculated before. Others will be new and exciting and fresh and different. So for instance, you see here in the list, we're going to be calculating range. Have you at some point in your life calculated a range?
Yes.
For quite some time. Variance? Maybe not. Standard deviation. Probably at least have heard of that before. Did it a couple different ways. And then there are a couple rules that we'll talk about as well. So first of all, dispersion. What are we talking about? Well, it's actually a very fancy word that just means we're looking at how spread out our data is. The degree to which our data is spread out, separated from each other. So basically, we're trying to answer the question, are all of our data points kind of honed in on one particular area? Or are all of our data points kind of spread out? Are they clustered? Or are they far away from each other? All over the place, as it were. If, of course, your data points are clustered in one particular area, that means you're going to have a smaller amount of dispersion. If, however, your data points are far away from each other, they're very spread out, then you'll have a larger amount of dispersion in your data. Now you'll notice there's some space to explain dispersion in your own words. So take a moment, write down, how would you explain this to, I don't know, your little brother or maybe your grandma. What does it mean to have dispersion in your data? Spread out. Go for it. Does that work for you? Now, before we continue any further in our discussion of dispersion, we need to make sure that there are two words that we all know the definition to. I suspect you do, but just in case. The first one is the minimum. Of course, the smallest number in your set of data. It, of course, has a partner. Its name is the maximum, which is the largest number in your set of data. I'm sure this is not new to you, but just in case. Alright, so we start out with our first measure of dispersion, which is very wonderfully called the range. The range, of course, as you may recall, is the difference between the maximum value and the minimum value. Now, when we say difference in math class, what does that mean we're going to do?
Right.
We do a little subtraction problem to figure out our range.
Let me answer the question first.
Now, of course, if we're going to subtract stuff, that doesn't mean we need to have numbers to do that with. So when you're calculating range, you do need to have on-page data. You can't do that with qualitative information. You can't subtract a Honda from a Jeep and have something left over. Also keep in mind that the range is not persistent. Certainly, if it's using the maximum maximum number, which could be an extreme, or the minimum number, which could also be an extreme, it's going to be affected if you have numbers that are very large or very small in your set of data. So the range is not something that is going to be resistant. All right, so let's look at an example. We have some test scores listed here. These, of course, are not percentages. They are the raw scores that one got on the test. And we want to find the range of the values. Of course, as we said, this is a subtraction problem, so we're going to take the maximum number minus the minimum number. So what is our maximum value in this list? And what is our minimum value? Yeah. So take 36 minus 16 and a half.
19.5.
Yeah. So we have a range of 19 and 1. Questions about finding the range? Now, clearly the range can be helpful. Gives you an idea of, how wide this set of data is. 19.5 points wide in this particular case. Knowing the maximum and obviously can give you an idea of how spread out the information is. But does the range actually take into consideration all the numbers in the set of data? Just the maximum and minimum. So there's only two numbers. We could have, 3,000 numbers in this set of data, and we only are getting the minimum and maximum. And so that's kind of limiting. And so statisticians started thinking about this. What else can we do to get a better idea of how every number in the set of data is spread out? Because, of course, the minimum and maximum could be really close to the other numbers in the set of data, or it could be very far away from the rest of the numbers in the set of data. So I started to think about this, and I thought, okay, well, of course, we can compare each number to each other. That could be a lot of work. I mean, you've got to compare the first number to all the other numbers, the second number to all the other numbers. That's a lot. And then they got thinking, okay, is there some kind of common number we could compare them to? And I said, well, we have these measures of center, mean, mode. Could we compare all of the numbers in the set of data to one of those? Well, probably wouldn't want to choose the mode, because the mode doesn't always happen in a set of data. Some data has no mode. So they decided to go with the mean. And they came up with this idea of variance. Please note, there's nothing on this slide, it's on your paper. So what they said is, hey, if we want to get an idea for all of the numbers in the sets of data, all the numbers in the data set, let's compare each of the numbers to the mean. See how far away each number is from the mean to make some kind of comparison as to how spread out the data actually is.
He said close your mouth. No, man.
And so what we determined, okay, we can take each number and we can subtract the mean from it to find out the deviations or the differences between each number and the mean. Notice, of course, we have a population option. We have a sample option. We can do it in either case. When they did that, they got to looking at it, they said, okay, well, mean, of course, is, balancing point. There's some numbers that are going to be less than the mean. There's some numbers that are going to be greater than the mean. It's kind of awkward to have negative numbers. So, well, it might be a good idea to get rid of those. So what mathematically could they do to get rid of negative numbers? Absolute value is one way. There's another way. exponential scheme due to a number that always makes a positive squared. And that's what they actually went with. They decided, hey, instead of having all these rands and negatives hanging out, let's go ahead and square these differences. So that way we get positive numbers. So they said, all right, once we subtract them, we'll square. Not a big deal. And then I realized, okay, well now we have this big list of squared things. Great, what are we going to do with that? Let's find the average of them. Let's find the mean. Well, that's what they did. And so they came up with the formula for variance. Now keep in mind again, since we're doing subtracting and squaring and stuff, you have to have quantitative data. And obviously since you're using the mean, which is not resistant, your variance is not going to be resistant either. So in order to calculate the population variance, we use a formula that looks like that.
What? I got no connection.
Why do you think that?
No, I'm just seeing what.
Now, of course, if there is a population variance, there also needs to be one for the sample variance. And it looks like this. First year, I took counting. And that's only because I took that second semester. That's only because I had gone in high school and I got much credit for it. Now, please note, just in case anyone is confused, apparently some folks were yesterday, this is the bar on the X for X bar, not a negative or something like that. It's just now, things of course look a little crazy up here, but I promise you it's not that confusing. Okay? As we saw on the last screen, we want to, of course, subtract each number from the mean. So remember, of course, x sub I is each individual number we have in the set of data, and we're going to subtract the mean from it. And then, of course, we're going to square it so we can have it all positive. Once we do all of that for every number in the list, what do we do with all of those numbers? What does that equal? We're going to sum. We're going to add them up. Once we add them all up, we are going to divide by n, which is representative of what? Population.
The number of
Population.
sample size?
That is not sample size. Population size, yeah. So how many numbers we have in our list? So essentially, we subtract each number from the mean and we square it, and then we find the average of them. We find the mean of them. We add them up and divide by how many there are. Now you'll notice in the sample there's a little bit of a difference. We're still taking each number and subtracting the sample mean. We're still squaring, we're still adding. But instead of dividing by n, we're dividing by n minus 1. So we have the sample size minus 1 as opposed to just the population size. We'll talk about why that is in a little bit. Questions about our formula? Alright, so let's try and see. Now, because we are taking each number and we have to subtract the mean from it, this process, this formula, really does lend itself to a table. And so I would encourage you, anytime you're asked to calculate a variance, you set up a table for yourself to make that happen. Now, again, as I mentioned, we're taking each test score that we have and we're subtracting the mean from it. What do we need to find first? Yes. So take a moment and find the mean.
Oh, no.
I just remember I was looking at the
Girl, how you they have you so bad. He said it. Well, he didn't say the home. He said home. We gotta come back here again. Come on, Ohio. We about to show the path in Ohio. I know I'm in college right now. School. Here. So we didn't have like
Alright, floating point in the beans. Alright, 26.6, then what you said? 1.8, so we need a consistency here. I got 26.6. Alright, we have mean of 26.6. If perhaps you neglected to get 26.6, perhaps either A, you typed something in wrong, or maybe you divide by enough numbers. Alright, so now that we have the mean, what do we need to do? What is the first step in our formula? Okay. So, first thing we need to do is say 35.5 minus 26.6. What do we get? Everybody else see 3.9? Okay. Alright, 31 minus 26.6.
4.5.
4.5?
4.4.
Alright, what happens when we take 24.5 minus 26.6?
24.5 divided by 2.
We can certainly have negative numbers in our subtraction column, yes. Alright, take a few moments, finish out your subtraction column.
You jump something. No, this one is something. I need bars.
I'm gonna take it back.
Depends how many ones are left.
We're gonna have all 4 left.
And we get 4 points.
Yours is on 3 on 1.
I put them usually on.
Okay.
Questions about the subtraction? Alright, so now that we've done our subtraction, what we gotta do next? Every time on has there. What we gotta do? We gotta square all of our numbers. Now, keep in mind, if we are trying to square something like negative 2.1, what do we need to do? Yeah, gotta put parentheses around it, so that way it squares appropriately, or, come on, well, just square 2.1 is gonna be this. So, when you square 3.9, what do you get? Everybody find the square button.
No worries.
19.30.
Where's square button? The x2 beside the exponent. Yeah, it's different. You got an old chunk. I don't know about that. You got the same one. The same one.
And yours actually,
You got
you're the only one with it.
Word.
Very fun. Finish your squarings.
I did. You really did. You said it's my sixth.
I'll do an inch. I trick back.
Absolutely no reason.
That was I'm going to sleep. He just told you to go to sleep. That's crazy.
I'm gonna send an email.
Whoa. He was playing the playoff game.
Maybe I should look at home.
Yeah, I see you in the hospital.
What about you? I think you're going to get there.
All right, so questions about the squaring. All right, so now that we are done squaring, yay, what is the next thing our formula tells us to do?
Divide by 10.
We're not dividing it. You're gonna add. Have those parentheses, obviously, squares, it's beside the summation symbols. That means all those squared things that we've done, we now need to add up. So we need to add up our whole squared column. So take a moment and add. Add up the squared column.
These are clear.
Billy Clay, I thought that about it.
Gentlemen, Brady, and you need to add.
I asked how much we had.
No, we're adding up the square. You ain't got the rule.
If you want to play, you better earn your spot. That's what I'm saying. If you're not earning, you're not doing nothing. Some people don't want to earn. Some people go to practice sometimes. Go to practice. You're talking about
All right, so when we get to our total,
55.82. I got it.
I got
55. I got 0.62. Oh yes, yes. I got 255.
now I suspect if you have a different number than that, you must have typed the number wrong.
Oh, I did my 26.
So 255.73, that is finally the numerator to this formula for the variance. What goes in our denominator? The n, what does the n represent? Population size. So what is the size of our population here? 8. 8 numbers in our list. So our population size is 8. Do some very fantastic division.
And the answer is 31.97.
Well, wait, is it 6 or 7?
Mine was 1.966, so I made it 9.7. Shut up.
Questions about finding the population variance for who we're finding out?
Shut up, cuz you hear the bell. You hear the bell too?
It usually works best if we simply take care of ourselves. Now, you'll notice that there is also an option here for S squared, which is the sample variance. Under normal circumstances, we would have either a population or a sample. We would calculate one or the other. Okay? But to save time, we're going to use the same information. We're going to calculate both, just so we can see the differences between the two. Okay? Again, under normal circumstances, we do one or the other, but we're just going to calculate the sample variance here so we can practice. So let's look back at the formula here for sample variance. When to go. So, as we compare, do we take each number and do we subtract the mean? Yes. Do we square all of those subtractions? Yes. We add them all up? Yes. Their numerators, of course, match. Now, granted, this one has a population mean in it, this one has a sample mean, but they match. So that means that all of the subtracting, all of the squaring, all of the adding is the same, regardless of which one we are doing. The difference, of course, comes right here in what we divide by. Okay? So instead of dividing by the sample size, we're dividing by the sample size minus 1. So let's go back to this process that we went through. Our sum, as we said, is still the same. But what are we going to divide by?
7.
Because 8 minus 1 is 7.
So that oh,
So I think it's 36 points up.
5, 3.
Hello?
Sorry.
Now, again, we would generally only calculate one or the other, but you can see that the only difference between the process of population variance and the sample variance is what you divide by. You have to go through the same process of subtracting, squaring, and all that. Now, you might be wondering, why is it for the sample variance we divide by n minus 1, whereas the population variance we divide by just the n? And there is a reason for this. Statisticians, when they started to divide this whole process of variance, they of course wanted to make sure that the sample variance was going to somehow represent the population variance. And so they started out by just dividing by n as well in both cases. That was the easiest thing to do, obviously. Can you stop? And so when they did that, they had to take a population of, say, 20 numbers. They would calculate the population variance, and then they would start taking small samples from that population and determine the sample variance to see if, in fact, the sample variance matched what they had predicted and what they had gotten for the population variance. And they found out, after doing this time and time again, that honestly, the sample variance, if you were dividing by n, did not really represent the population variance. There was a discrepancy there. What they found is that the sample variance is actually biased. What does that mean? Well, it means that, just like bias in the real world, you're preferred one way or the other. It's actually overestimating or underestimating the population. And so, again, they found that as they were dividing by just n for their sample, that the sample was not matching the population. There was this bias that existed. And that, of course, is a problem, because if we're using the sample to represent the population, but it's not representing the population, we got an issue.
Provides up to unfair advantage, does that count?
I mean, that's, kind of the general definition, but in this case, what is an unfair advantage statistic? It's overestimating your interest. And so what they did, they started looking at options, and they decided, okay, well, turns out that if we divide by n minus 1 instead of n, it actually does represent the population. So that's why we divide by n minus 1 in the sample instead of just the straight up n. That n minus 1 is known as the degrees of freedom. Now, why in the world would they call it that? Well, here's the thing. You have this list of numbers, okay? It's a sample of, 10 numbers. Numbers 1 through 9 really have the freedom to do whatever they want. When you get down to number 10, if that list of numbers is actually going to represent whatever the population is, that last number does not have the freedom to do whatever it wants. It has to be either so much or so little so that the sample represents the population. It's kind of weird to think about numbers choosing, but it's kind of what we're doing. Think about it this way. If there is a radio contest going on, right, they're giving away 3 sets of movie tapes. Let's say a comedy, an action film, and horror film, right? People get to call in, and so the first caller gets to choose whatever they want, second caller, etc. So first caller calls in, what do they get? Which one do they choose? Horror. Horror, okay? So first caller calls in, they get to choose horror from the 3. Second caller calls in, what do they get to choose? Comedy. So they get to choose comedy from either the comedy or the action film. Third caller calls in, what do they get to choose?
One option.
They only have action left, so they don't get a choice, right? They don't have the freedom to choose to do whatever they want. They're stuck with whatever everybody else didn't pick. And that's what it means to have degrees of freedom. Caller 1 had freedom, caller 2 had freedom, caller 3 did not have any freedom. They're stuck. Same thing with numbers, okay? If that sample is going to represent that population, that last number is not free to be whatever it's going to be if it's going to represent the population. So we divide by n minus 1 instead of n to compensate for that. Questions? All right, take a moment then and explain that degrees of freedom thing in your own words. James, are you planning?
You get up on 10:30. I'm already going shooting right now.
No, I don't know. I think they did work, but my friend actually failed. Yeah, like my friend, she was like, and I got it for one time, and then she told me she didn't really think that this was actually good, but my own leader, and that's not it. You know, with the free that would be, you know, the one, or like, I guess, values wouldn't have.
Right, one value is not allowed to be whatever it wants to be. If All right, guys, so at this point we are going to stop our notes because we do have some presentations that we need to listen to today. So, at this point, what we need to do, number 1, is return calculator. Number 2, put notes in a safe place. And I will go ahead and pass out the blank.
Thank you, Ms. Stetar. You are so close.
We're breaking.
I got to go take over.
Gotcha.
This is the last thing we're doing for class.